Now, if the electron configuration has partially filled subshells, it's possible to write more than one Slater determinant. Okay, so it's each Slater determinant corresponds to one quantum state. So one way that one quantum state, you can think of it as one way that the atom can have that electron configuration. What's the degeneracy for each electron configuration? How many ways can an atom have a particular electron configuration? The way to figure it out is you draw orbital diagrams, or you can create a table to examine all the possibilities. Okay? And if you only have one partially filled subshell, the number of ways, which will be the degeneracy, would be equal to the number of spin orbitals factorial for that partially filled subshell, divided by s factorial times s minus n, where n is the number of electrons in that subshell. And if you have more than one partially filled subshell, then you have to multiply the number of ways that you can assign electrons to each one of those subshells. So let's look at an example. 1s1, 2s1. Okay. How many ways can you assign 2 electrons to the 1s and the 2s orbitals? We're having 1 in each. Okay, for how many ways can you assign 1 electron to a 1s orbital? 2 ways, right? So n1s in this case is going to be, okay, let's look at the number of spin orbitals here. How many spin orbitals can you have in the 1s? It's 1s alpha or 1s beta, right? So that's 2 factorial over two factorial times 2 minus 1 factorial, and that gives you I think I might have this formula mixed up. Okay, this should be n factorial. Sorry, that's n factorial. Please correct that. This should be n factorial. Okay, so that's 1 factorial divided by 2 factorial, 2 minus 1 factorial. So what would that be? That's 2 factorial divided by 1 factorial times 1 factorial. That's equal to 2. There's 2 ways. Okay, it's either spin up. You have 1 electron. That electron can either be spin up or spin down. So this is 2 ways here. So n1s is 2 ways. Okay. How many ways can you put 1 electron in the 2s? It's either spin up or spin down. So how many total ways can you have a configuration of 1s1, 2s1? 2 times 2, which would be 4. Okay. And let's look at those possibilities. You can have 1s bar, right? And okay, bar means spin down. Let me use that abbreviation. 1s bar is the same thing as 1s beta, and then I'm going to say 1s is the same thing as 1s alpha. And you can have 2s bar. Okay? So you can have 1 here and 1 here, right? You can have an electron in the 1s orbital spin up. The electron in the 2s orbital can be spin down, right? The electron in the 1s orbital can be spin down. The electron in the 2s orbital can be spin up. The electron in the 1s orbital can be spin down, and the electron in the 2s orbital can be spin up. It's 4 ways. Okay? Here's another way of looking at it. This might be easier to visualize. 1s, 2s, right? So this could be spin up, and that could be spin up. This could be spin up, and that could be spin down. You can have one electron here that's spin down, the other one up here would be spin up, and then the last possibility is it's spin down here and it's spin down. So there's 4 possible Slater determinants you can write. What are those 4 Slater determinants? Let's call this D1, D2, D3, and D4. Determinant 1 would be what? 1s alpha and 2s alpha, right? 1 and 1s alpha 2, 2s alpha 2. Remember, when you write your Slater determinant, this is the first spin orbital, 1s alpha, and this column would be the second spin orbital, that would be 2s alpha. So that's your first Slater determinant. So there's 4 Slater determinants you can write for our configuration. That is 1s1, 2s1. All right. What about a 1s1, 2p1? How many ways can you, how many spin orbitals can you have in a 2p subshell? 6 spin orbitals, right? And if you want to distribute 1 electron there, so 1 factorial divided by, divide by 1 factorial, so this is your n, right? And s minus n factorial, so 6 minus 1 factorial. How many ways can you distribute 1 electron? Can you assign 1 electron to the 2p subshell? 6 factorial over 1 factorial, 5 factorial, that's 6 times 5 factorial over 5 factorial. And that should give you 6. 6 ways. What are those 6 ways? So it can be here, spin up, right? Another way would be here, spin up. Another way would be here, spin up. What's another way? The other way would be spin down, right? So it can be spin down here, or it can be spin down here, or it can be spin down here. So how many total number of ways how many Slater determinants can you write for this then? 2 times 6. 12 possible Slater determinants. You can tabulate those. Okay, you can say 1s. In the 1s, it can be spin up or spin down, right? In the 2p, it can be 2p plus 1, 2p plus 1 spin down, or 2p0, or 2p0 spin down, or 2p negative 1, or 2p negative 1 spin down. Right? So electron 1 electron could be here, and the other one could be here, there. 1s spin up, 2p0 spin up, 1s spin up, 2p0 spin down, 1s spin up, 2p minus 1 spin up, 1s spin up, 2p negative 1 spin down. So 6 ways, and then the other 6 ways would be this, this, that, that. So you get 6 times 2, 12 ways. Okay? So how many Slater determinants can you write for the ground configuration of carbon? Let's tabulate those. How many electrons do we have? 6. Now, 1s2, 2s2. We have 1s, 1s bar, 2s, 2s bar. Okay? Those are filled. There's only one way to have those filled, with everyone having just 1 electron. Okay, so don't worry about filled subshells. When all your subshells are filled, for example, there's only 1 Slater determinant you can write. Okay? It's only when you have partially filled subshells that you can have more than 1 Slater determinant. So in this particular case, we don't even worry about this one. We're just going to worry about how many ways can you assign electrons, 2 electrons to a 2p subshell. So you have 2p plus 1, 2p plus 1 bar, 2p0, 2p0 bar, 2p minus 1, 2p minus 1 bar. How many ways can that be? Let's look at the formula. Formula was, how many spin orbitals do we have? 1, 2, 3, 4, 5, 6 spin orbitals. So 6 factorial divided by, how many electrons do we have to distribute? So 2 factorial times 6 minus 2 factorial. And so that gives us 6 factorial divided by 2 factorial times 4 factorial. And that gives us how much? 6 times 5 times 4 factorial divided by 2 factorial, 4 factorial. 4 factorial cancels out. That's 30 divided by 2, 15 ways. What are those 15 ways? You can have one here and another one there. So that's one way. What's another way? One here, one there. What's another way? One here, one there. One here, one there. 2p plus 1 and 2p negative 1 bar. So that's the first 5. What else can we do? Start with the second one. I don't need to do this anymore since it will be duplicating, right? So I don't do that. We have 2p plus 1 bar, 2p0. What's the next one? 2p plus 1 bar, 2p0 bar. What's the next one? 2p plus 1 bar, 2p negative 1. The next one would be 2p plus 1, 2p negative 1 bar. How many ways do we have so far? Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9. 6 more to go. What else can we do? 2p0, 2p0 bar. So that's number 10. Let me put this grid on so I can. So that's number 10. Number 11 would be what? 2p0, 2p negative 1. Number 12 would be 2p0, 2p negative 1 bar. Okay. What's the next one? 2p0 bar, 2p negative 1. And then 2p0 bar, 2p negative 1 bar. Okay. So that's number 13 and number 14. What would be number 15? Number 15, you're going to have negative 1 bar. 15 different ways. Okay? So we say that the ground electron configuration of carbon in the orbital approximation, using just the electron configuration, that configuration corresponds to a degeneracy of 15. There's 15 ways you can have that kind of electron configuration.